Okay, cool. So today we are going to be discussing problem solving, and basically, discussing problem solving basically means that we are going to be looking at some theory, and if we have time, we are going to be doing some number theory as well. It's the opposite. Sorry, we are going to be looking at the theory, and if we have time, we'll do problem solving. Okay, cool. I guess we can start now. So the first thing that we are going to be discussing is binary exponentiation. So we all know how exponentiation works, right? Obviously, we all know what exponentiation is. It's basically just taking a to the power of b, right? If you want to take a to the power of b, then use, well, exponentiation. Okay, one second. Let me go back here. Okay, so let us say we want to take 5 to the power of 3. Then in this case, this would be equal to 5 into 5 into 5, right? Let's say we want, on the other hand, 5 to the power of 10, right? 5 to the power of 10. This would be 5 into 5 into 5 into and so on for 10 times. It would be this for 10 times, right? So clearly this is what exponentiation is. Everyone already knows this. Power function can also be used. So Nikhil, the issue is, I will discuss this soon, but issue is, what is the time complexity of this? Can someone tell me what's the time complexity of just multiplying something for n number of times? Like if we have a to the power of b, then what's the time complexity of this? Any idea?
O of b.
O of b. Exactly. That's exactly right. Nikhil also got it. And yeah, everyone's getting it. Cool. So this is the time complexity, right? So the time complexity is clearly O of b because we are doing this for b times. Now the issue is, like generally we don't take any number a to the power of like a very, very large number. This generally doesn't happen, but there is something called modular exponentiation, modular expo, right? We'll come to that later. Like we will also discuss this today. Don't worry. But like the thing is, let's just assume that b can be very large. If b is very, very large, obviously this is going to overflow, right? Clearly this is going to overflow, but let's just forget that. Let's just forget the overflow. Let's just think about this, right? Let's just think about this. So if I wanted to take take the power of this, let's say I add 2 more zeros. This is 10 to the power of 9. So this is a to the power of 10 to the power of 9. This would be big O of 10 to the power of 9, right? So it would be 10 to the power of 9 operations, which is pretty big, which is very, very big, right? So it will take too much time. And the issue is that the inbuilt power function, never ever use this. Never ever use this power function because first of all, it is also O of b. Like the method we are going to be discussing converts this O of b to O of log n. So I will tell you how to do that. Log n is basically log b here, right? Log 2b. Now, on the other hand, though, let's come back to this power function. This power function is first of all O of b, which is bad in and of itself. And the second thing is that this is for floating values. This is for floating values. So there are two things that happens. There are two things that happen when you take power of a comma b, right? So what happens is that this takes O of b time. This converts a and b to a float as well. This converts a and b to a float as well. And then it gives you a to the power of b as well as a float, right? It gives you this as a float as well. So a to the power of b is a float. It converts a and b to a float. It is also big O of b. And well, if a to the power of b is a float, then this basically means that there are going to be precision errors, right? So precision issues will happen if you take a to the power of b as a float. Generally, if you use float where an integer should be used, you are going to get some precision errors, right? So yeah, so never ever use this power function because it's just bad in every single way. So if you're just taking the power of 2 integers, never use this. Okay, so yeah, first of all, we'll just say never use power function, never use the power function. If you want to take power, always implement your own power function. We will discuss this. Okay, now let's get to how we can do binary exponentiation. Okay, in binary exponentiation, basically we can just make some observations. We can make some simple observations, which is, let's say I have a to the power of b again. I have a to the power of b. And if I have this, then this basically means that it's equal to a to the power of b by 2 times a to the power of b by 2. Right. So if I multiply a to the power of b by 2 into a to the power of b by 2, well, this is just going to be equal to a to the power of b by 2 plus b by 2 which is equal to a to the power of b, right? This is just a to the power of b. So this is true for any value. Clearly, this is true for any value. But in C++, there's an issue, which is that division gives you an integer, right? If you are dividing an integer by an integer, it gives you another integer. So yeah, if you take b equal to 5 and you divide it by 2, you'll get 2 as the result, right? So b by 2 when b equal to 5 would be equal to 2. So what we can say is this will only happen. This is only true if b is even. So b is even, right? Otherwise, if b is odd, then simply we just have to take a to the power of b. Okay, let me just add the floor symbol for this. This is the floor symbol, by the way. So if you are flooring something, you put like 2 lines and you put that below. If you want to seal, you take 2 lines and you put it above like this. So that's the seal function. Okay, so if you want b to be odd, then you can take floor of b by 2 again times a to the power of b by 2 again. And finally, what you can do is just multiply again by a, right? So what this will do is this will be equal to floor of a to the power of b by 2 plus a to the power of b by 2, which will be, if b is odd, then clearly this is going to be b minus 1, right? So if I take, for example, b equal to 5, let's say we have b equal to 5, and I take b by 2 plus b by 2, this is going to be equal to 2 plus 2 equal to 4, which is equal to 5 minus 1, right? You can test this with any value. If I take, for example, 123, that's going to be equal to 61 plus 61, which is equal to 122, right? This is equal to 122. So we again have 1 less than the actual value. So this will be a to the power of b minus 1. And that is why we are also multiplying by a. So we'll take a to the power of b minus 1 times a, which will be equal to a to the power of b again, right? So is this observation clear to everyone? Like, first of all, if you take b as even, then it's a to the power of b equal to a to the power of b by 2 into a to the power of b by 2. And if it's odd, then you do the same thing as the even one, except you also multiply by a. Okay, is this clear to everyone? Any doubts here? Okay, please let me know with +1 in the chat if this is clear. Okay, Ankit and Nikhil have got it. Naveen as well. Aditya, Atish, Piyal. Okay, everyone has got it. Odd repeat. Oh, okay, sure, Akash. I will repeat odd ones. So if you have b equal to, let's say, 7, then we want to split this a to the power of b into half, right? We want to split b into half. But the issue is, if you split that for an odd number of b, so if b is odd, then in this case, you get a to the power of 7 equal to a to the power of 3 into a to the power of 3. But clearly, this adds up to 6, right? So if you take by 2, that will be 3. We can't take 3.5. There's no reason to take 3.5. We won't be taking 3.5. So we'll take a as 3 and a as a to the power of 3 again. And then we multiply by a once more, just so that it adds up in total to 7, right? So we'll just do that once more. So this is the idea behind odd. Okay, I hope this is clear now, Akash. Okay, now we haven't discussed recursion yet. I know we haven't discussed recursion yet. We will be discussing it in the future. But for now, let's just look at a basic idea. This should be pretty simple. So there will be no issues here. But I will just show you the basic idea. Let us say I want to take a to the power of b, right? This is just equal to, we know, a to the power of b by 2 squared, right? This is just a to the power of b by 2 squared times a if it is odd, else it's or it's equal to nothing. It's times 1 if it is even, right? So if it's odd, I need to multiply by a, otherwise I don't multiply at all. Now, if a to the power of 0 is taken, so if I get to a to the power of 0, then always this is going to be equal to 1, right? So a to the power of 0 for any a is going to be equal to 1. A to the power of 0 is 1. Now, 1 second. Let's try to implement this in code, right? Yes, Ankit, you are exactly right. This is in fact the base case. Now, what I'm going to say is I'm going to take in power of int a comma int b, right? So don't name it pow, by the way. Please don't name it pow. This will be very confusing for you in the future. And you might get some compile errors as well sometimes. So just name it power or exponentiation, so exp or something like that. So I'll just take power here. Now, if b is equal to 0, so if I take if b is equal to 0, well, I'll just return 1, right? I don't care what a is. If b is equal to 0, then I immediately return 1. Otherwise, I'll take in half power equal to power of a comma b by 2. Right? Half power is power of a comma b by 2. So what I'm saying is half power, I'll just write hf, is equal to a power b by 2. Right? Now I will say, if a modulo 2 is equal to 0, then return. So this will return the value to the previous column, right? So what I'll say is a to the power of b equal to a to the power of b by 2 squared and times a or times, I don't care about that. For now, let's just ignore this part, right? And in a to the power of b by 2, what I'll say is this a to the power of b by 2, it will be a to the power of b by 2 by 2, right? Or basically a to the power of b by 4 squared. So what I'm saying is a to the power of b is actually equal to a to the power of b by 4 squared and squared again. Right? Now, again, there'll be times a, sometimes there won't be times a, sometimes. Let's just ignore that for now. But basically, you can see that this just goes in deeper and deeper, right? So the next step would be a to the power of b by 8 whole squared, and squared. I'll just write it on top like this. So squared, right? And then it will be by 16 squared again, and so on. Right? Basically, I'm just taking a to the power of b by 4. I'm taking half power, and I'm taking the power of that. I'm taking the power of that value, right? So half power equal to power of a comma b by 2. Now, if a modulo 2 is equal to 0, I'll just return, okay, sorry, b modulo 2 is equal to 0. I'll just return half power times half power. That's it. Otherwise, I will return half power times a, right? So for example, let's try to dry run this. Let's try to dry run this with a value, let's say 13. Right, so I want to find the power for 13. Now 13, let's say I want to take 2 to the power of 13. The a value doesn't really matter. Like a value can basically be anything. What's important is b. So 2 to the power of 13 would be equal to 2 to the power of 6 multiplied by 2 to the power of 6 multiplied by 2, right? Because this is odd, I'll take a to the power of b by 2, a to the power of b by 2 times a. Now, 2 to the power of 6 can be replaced with basically 2 to the power of 6 whole squared times 2, right? Now, what I can do next is say 2 to the power of 6 is just equal to 2 to the power of 3 squared, right? 2 to the power of 6 is also equal to 2 to the power of 3 squared. Okay, let me just do this again. So here we would take 2 to the power of 6 equal to 2 to the power of 3 whole squared. So over here, I can just substitute that value and I will get 2 to the power of 3 squared. Now, what is 2 to the power of 3 squared? Well, for that, let's figure that out again. 2 to the power of 3 squared. Well, let's first calculate 2 to the power of 3. That would be equal to 2 to the power of 1 into 2 to the power of 1 into 2 to the power of 1, right? Or basically into 2. And 2 to the power of 1 is equal to 2 to the power of 0 multiplied by 2. Right? Because this is just by 2 again. So we'll take for 2 to the power of 1, we'll take 1 by 2, 2 to the power of 1 by 2, which should be equal to 0 times 2 to the power of 1 by 2, which should also be 0. And since 1 is odd, we'll take times 2, right? So basically we get 2 to the power of 1 into 2 to the power of 1 into 2. And well, we'll take this value. We'll say, okay, this part is 4 and 4 into 2 is equal to 8. So 2 to the power of 3 is equal to 8. And now I will say inside this, I'll say, okay, I have the value of 2 to the power of 3 and that is equal to 8, right? So 2 to the power of 3 is equal to 8. And if I take 8 squared, I get 64. Now, if I take 64 squared, I'm pretty sure we get 1024 or something. Okay, I'm not very sure actually. I'll paste 64 into 64. Oh, it's 4096. Okay. So here we get 4096, right? So 64 squared is 4096. If I multiply that by 2, I get 8192, right? And let's make sure. Let's take 2 to the power of 13. And there you go. It is in fact 8192, right? Okay, Vineet is asking, can half power be equal to? Okay, that's a good question, Vineet. Can we take, instead of half power, that won't be half power, let's just name it power value or something, right? Vineet is asking, can we replace this half power equal to power of a comma b by 2 into power of a comma b by 2? Now, this is a good question, but there is a small issue with this, right? We will see the issue soon. But for now, let's just look at how this would work. Like, let's take the previous example. Let's take the previous example and see how this will work, right? So first, I'll be at b equal to 13 or something. Then I'll go to b equal to 6, then to 3, then to 1, then to 0, right? So this is the process. So I'm dividing by 2 each time. Now, can someone tell me the time complexity of this entire line? Like if I have b, then I go to b by 2, then I go to b by 4, and so on until I get to 0. What will it be?
Log n.
Log n. You are exactly right. Okay. There you go. Everyone has got it. This would be log n or log b basically, right? And I hope this is clear to everyone because we are dividing by 2 each time. We are basically taking, instead of going to 0, let's say we are going to 1. Then in this case, we just take b to the power, b divided by 2 to the power of k, which is k is the number of times this operation is repeated, is equal to 1, right? Then we have b equal to 2 to the power of k, or log b base 2 equal to k. And now the number of operations k is equal to log b, right? So this is the proof basically. So this is completely fine. Now notice that we have just converted our entire power function from O of b to O of log n, right? Which is huge, log b, which is huge, right? And it's very simple. We are just using a simple fact that if you take a to the power of b, that's just 2 like repeated values of a to the power of b by 2, right? Is this clear to everyone? Any doubts here? Okay, if anyone has any doubts regarding this, if this is not clear, please do let me know. Like, I know it looks magical, basically, but the simple idea is that if I want to take a to the power of b, or let's say a to the power of 10, I just want this to be equal to a to the power of 5 into a to the power of 5, right? And if I can calculate a to the power of 5, like you can just try this by hand. Like if you want to do this, you can just try this by hand. Like if you want to calculate 5 to the power of 10, you take 5 into 5 into 5 into 5 into 5, let's say, or you're just, let's say you just did this, you just calculated the value of this, then you'd say, okay, I'm too tired to do this. So what I'll do is, if you want to enter this into a calculator, you'd first enter 5 into 5 into 5 into 5 into 5, let's say, and then you'll say, okay, well, I already have calculated this half of the thing. I'll just have to multiply it by the same thing again, right? So you'll just say that, okay, take this value as equal to something, I don't know. So this would be 625 into 5, which is 3125. So I know that this is 3125. So you'll just say that, well, I'll just take 3125 into 3125, right? I'll just take 3125 into 3125. And that would be much simpler. So you don't have to redo the whole thing because you already know the value. You already know the value. So you can just multiply it by the same thing, right? And if you take 5 to the power of 10, that's 9765625. And if you take, let's say, 5 to the power of 5, which is 3125 into 3125, you can see that we again get 9765625, right? Which is the same value. So yeah, this is how basically binary exponentiation works. You just take half of the thing and you just multiply it to get to the original value. That's it. It's as simple as that. Okay, now let's come to what Vineet asked. Vineet asked something, right? Vineet asked, can we just take this is equal to power a comma b by 2 times power a comma b by 2? And now since we are multiplying this already, we don't have to take this. We can just do this, right? We can just take return the value. I'll just take value here. It's not half power, it's full power basically. So we'll take value and something like that. Okay. Anirban is asking, shouldn't we initialize half power equal to 1 and then multiply with power a comma b by 2. No, that's not necessary, Anirban. Why would that be necessary? Okay, you can type it in the chat while I will be discussing this. Okay. Now, the value equal to this thing. Can someone tell me the time complexity of this one? Any idea? What's the time complexity of this now? Can someone take a guess?
Linear.
Linear. That's exactly right. I know this looks weird, but this is actually linear. Now, just adding this power statement again, that makes it linear. Because let's try to think about it in two ways. Let's try to think about it intuitively, logically, and mathematically, right? First, let me do it intuitively. So what does the power function say? The power function of a comma b says, a to the power of b says, find the value of a to the power of b. And to find that, it takes a to the power of b by 2 squared, right? Now, the issue is that this is a function. This is a function of a comma b. And this is saying take function of a comma b by 2 times function of a comma b by 2. Now, what happens is that when you are taking this twice, right? When you're taking this twice, the same thing twice, it's basically like, let's say you want to find 5 to the power of 10. Then you're saying, okay, I want to calculate 5 to the power of 5 first. So you calculate 5 to the power of 5. Then you're saying, okay, I want to calculate 5 to the power of 5 again. Right? So that's what you're saying. So you're saying calculate a to the power of b by 2. And you're saying again calculate the a to the power of b by 2. So what's the point now? What's the point? Like, it's the same thing, right? If you're taking 5 to the power of 5, you are not actually using the same value again. You're not using the same value again, but rather what you're doing is, okay, exactly, Ankit, you're doing the same thing twice, which basically means that if you take 5 to the power of 5, you are saying, okay, I'll calculate 5 to the power of 5, it will be 5 into 5 into 5 into 5 into 5. Then you're saying, oh, I want to calculate 5 to the power of 5 again. So it will be 5 into 5 into 5 into 5 into 5, right? Which basically negates the entire thing. So what you did basically negates the entire thing. So you are calculating this once and you're saying, okay, I'll calculate it again. So if you think about this mathematically, let's see what happens. Let's take a power of 2 so that it's simpler. So let's say we have 16. Then before we went to 8, then we went to 4, then we went to 2, then we went to 1. But now what will happen is from 16, we'll go to 8, but we'll go to 8 again. From 8, we'll go to 4. Then we'll go to 4 again. And from this 8, we'll go to 4. This 8, we'll go to 4 again. This will be 2. This will be 2 again. This will be 1. This will be, this will be 2. This will be 2 again. Right? And finally, we'll have 1, 1, 1, 1, and so on. So basically, you have not, okay, this will all be 1. So you can just imagine that. Now you can see that we have basically 8 values of 2. In other words, 16 values of 1, which is just O of n, right? So from 16, we are recalculating the same value twice. We are saying, okay, find the solution for 8, which also finds the solution for 4, but it does everything twice. So since it does everything twice, it's just copying it. It's just dividing by 2, and again, it's multiplying by 2, right? So it's dividing the value by 2, but then since it's doing it twice anyway, it's just multiplying the value by 2. So at each step, we divide it by 2, we divide b by 2, but the total time complexity doesn't change because we redo the same thing, which just multiplies it again. So in total, it's just O of n. Is this clear? Does this make intuitive sense to everyone? Like, again, you can just take this example. You can say, what is the value of 5 to the power of 10? Right? Before, what you did was you calculated this value and then you squared it. You took 3125 and you squared it, which is just basically O of 1. Squaring is O of 1, right? But what you're doing now is saying, okay, I want to calculate 5 to the power of 5 and I want to calculate it again. I want to calculate 5 to the power of 5 again, right? So if you do that, then that's an issue. If you do this, it's an issue because, well, you're doing the same task again, which in total will be n, right? So in total, finally, it will be n. So yeah, I hope this makes sense to everyone. Please let me know it like a +1 or -1 in the chat. If it's not clear, please do let me know right now. We'll be discussing recursion in way more detail and way more, like with more ideas and all of that in the future. But hopefully this gives you a basic idea of recursion and also, just shows you how this works. Okay, cool. And you can see that this is very, very simple and intuitive, right? Oh, can you show the correct code? Yes, I will show the correct code. This is the correct code. You can see that this is extremely simple. Like you just take, if b equal to 0, return 1. Always put this at the top, by the way. You should always put this at the top. Then you'll say int half power equal to power a comma b by 2. So you'll take power of half of the value. Then we'll forget how this works. We'll forget how it figures out the value. We don't care about that anymore. So we got half of the power. And so I'll say if b modulo 2 is equal to 0, return half power into half power. Otherwise, half power into a. And that's it. That's the power function. So you can just do this, and this will instantly be O of log n. Right? And O of log n is extremely small. So let's take the case where we talked about, like we said, what if we took a into 10 to the power, a to the power of 10 to the power of 9, right? So in this case, what we can just say is the time complexity before was 10 to the power of 9, but now it's going to be 32 or 30. It's actually around 30. So what was 10 to the power of 9 operations just got converted to 30 operations, which is an insane amount of gain, right? Like you basically are doing no work anymore. So you were doing so much work before, this would have taken 10 seconds, but now it takes like 0.0000001 seconds. A lot of zeros and then 1 seconds, right? Does the power function use this method? Unfortunately, no, Samarth. The power function does not use this method, and that's why you should never use it. It's extremely slow. Yes, Srihari, you basically use this when you find that a problem asks what is a to the power of b, but it's generally even more useful when there is modulo involved. Okay, I'll come to that in a second. But yeah. Iterative power function also take log n, like the recursive one. Yes, Sankit, there is an iterative power function, but like it's actually a bit hard to describe, like the iterative power function. You can look it up online. You can try to figure this out online. But if you have time, we'll discuss this. But basically, it's harder to grasp than normal recursive solution. Okay, Nikhil says in the odd case, first recursion call will be made from else part and further calls will be made from if part, right? Not necessarily. Let's say we have 15, right? Let's say we have 15. Then in this case, you will actually go to 7 after that. And after that, you'll go to 3. And after that, you'll go to 1. Notice that at no point are you reaching an even number except at 1. From 1, you go to 0. But, well, no values even here, right, Nikhil? So you cannot say that it will be, in case of odd, it will go to an even from the next call or anything like that. Because if you take 15 by 2, that will be 7, which is also odd. By 2, it's 3, which is also odd, and so on.
Hi, Shrivik. I have a question here.
Yeah, go ahead.
When you said we use this when we are going on, like when we need to solve for the modulo exponent thing, right?
Yeah.
Modulo problem. So that means like something like a problem that requires in the order of 10 to the power of 9 or something.
Yes, something like that. So in some problems, let us say that you want to calculate in some problems, let's say you just have to calculate some a to the power of very large value, modulo 10 to the power of 9 plus 7. How can you do this?
Okay. So we bring this method in to calculate that.
Yes, something like that. Yes, because generally, if the problem only asks for normal powers, then about 2 to the power of 64, if you take 2 to the power of even 63, this is the long limit, right? You can't go above this. So if you're not taking modulo, this is the maximum value they will give you. Because if they give you anything larger than this, then that won't work, right? Like you can't even store it in C++.
Okay.
So if it's only 63 values, then the improvement is very marginal. So what happens here is you get, instead of 63, you get 6 operations. So instead of 63 operations, you go to 6 operations, which is big, which is also big, but not as big as 10 to the power of 9 to 30, right?
10 to the power of, yeah, okay.
Yeah, so this is a much bigger difference.
Okay, got it, thanks.
Yeah.
Excuse me, sir.
Yeah, go ahead, Anirban.
Sir, in that you have done that half power is equals to power of a comma b by 2.
Yeah.
So, sir, every time the compiler comes, it will again recall that int power int a int b function from this question itself.
Yeah.
So, sir, my question is that it wouldn't execute that if b mod equal to 0 ever, no? Because every time it reaches it will again call that function, keep on calling, and finally when b becomes equals to 0, it will return 1 only.
Yeah. So what will happen is basically, okay, let me take Akash's example, 2 to the power of 17. Let's do two birds in one stone, and I'll show you how this works. Okay. So if you take 2 to the power of 17, and you go from 2 to the power of 17 to 2 to the power of 17 by 2, which would be 8, right? Now you'll take this value, you'll take the solution for this, you'll square it, you'll square this value, result, and then you'll take times 2. So let's just do that later. From 2 to the power of 8, we'll take 2 to the power of 4 squared again, and there's no times 2 now this time. So from this, we'll go to 2 to the power of 2 squared,
Yeah.
and then we'll go to 2 to the power of 1 squared, and okay, from 2 to the power of 1, I go to 2 to the power of 0 squared times 2, right? So we'll take this times 2. Now what's happening is that when I reach this code, when I reach 2 to the power of 0, it calls this, it goes to this if statement. If statement, if b is equal to 0, it returns 1, right? So what happens is the power function called in from, let's say here, b was equal to 1, right? If b was equal to 1, this would have called power of a comma b by 2, which would have called, this calls b equal to 0. Now, after it calls b equal to 0, it immediately gets returned the value of 1, right? So it gets returned the value of 1. So what it says is, okay, I won't call this again. I already called this once. The value is clearly 1. So it will say this is equal to 1. Right, Anirban? Does it make
Yes,
sense?
sir. Yes, yes.
Yeah, it doesn't go infinitely. After this evaluation is done, it goes to the next statement. So after this is done, it goes to the next statement if b modulo 2 is equal to 0 and so on.
So basically, that with the last one, 2 to the power of 0 is the base case, right? Like in terms of recursion.
Yes,
After-
exactly.
Yeah, then it takes that value and goes upwards.
Yes, exactly. So what happens here is this is the base case. Base case basically means that, well, it's the final value, it's the final result. And here we get this value as 1. So we get this value as 1. 1 square is 1. 1 times 2 is 2. So what it will say is this value is equal to 2 here, right? So it will take this 1 square would be equal to 1, and 2 to the power of 1 will be 1 into 2. So it will say I'll replace this value with a 2. So it will take 2 to the power of 2, which would be, well, 2 into 2, right? Because we know we already have 2, and 2 squared, we know we can take 2 into 2 for this. That will be 4. Now it will take this 2 to the power of 2 over here and replace this with 4, right? Like we know that 2 square is equal to 4. Now it will take 4 square. Well, that will be equal to, that will be equal to 4 into 4, which is equal to 16, right? Clearly that's equal to 16. So then it will say, well, I'll take 16 over here, right? I'll take 16 over here and it'll take 16 square. Now 16 square is 256. So it will take 256 squared into 2. So what's 256 squared? Let's see. That's 65536. I'm not going to write it down. And we'll multiply it by 2, we'll get 131072. Right, so we'll get 131072. Now let's calculate what 2 to the power of 17 is. There you go. It's 131072. Right. Don't worry, Samath. I know it's a bit confusing, but in the next class, we'll discuss this properly. Like I'll go from the very, very basics. Like this is, I am not discussing this in a lot of detail because, well, this class is not meant for recursion. But yeah, we will discuss this in a lot of detail, and I promise you this won't feel confusing at all after the recursion class. But yeah, for now, just this should make intuitive sense, right? Like you should probably feel like this would work. So yeah, that's good enough for now. Next class is for recursion. No, not really, Krishna. Like I'll figure out the details, like, but it depends. Like it will be very soon though. The next class for recursion will be very soon. Okay, let's move on, I guess. Okay, this is the recursive thing. Okay, that's done. Now, let's actually discuss the modular arithmetic. Let's discuss modular arithmetic now. And let's see how we can calculate a to the power of b modulo m. Okay, now, does everyone remember how we took modulo of a into a last time? Can someone tell me what this is? So if I take a into a modulo m, what will be the value? Like, how can we simplify this?
To a modern whole modern.
Sorry? Oh, yeah, okay, yeah. So it's a modulo m times, in parentheses, into a modulo m, modulo m, right? So this was clearly a modulo m into a modulo m, modulo m. Okay, Srihari, the screen is not visible. The screen is visible to everyone, right? It should be visible. Okay, I think for Srihari, it's not visible. I think there's an issue, Srihari, with from your side.
Okay, thanks. I'll check. Sorry.
Yeah, you can just leave and rejoin. I guess that would probably fix it.
Oh, okay.
Okay, so yeah, so basically a to the power of b modulo m is just equal to a into a modulo m. Okay, so we'll take a square over here for b equal to 2. So that would be a modulo m into b a modulo m, right? So that's it, basically. Now, if I had a to the power of 2, then let us say that I know a is less than mod. Let's say I know that a is less than mod, right? If I'm guaranteed that a is less than mod, then we know for sure that a modulo m into a modulo m. Here, clearly, I don't need these modulos, right? Does this make sense? So if a is less than m, I don't need the modulos over here. Because if a is less than m, this isn't necessary, right? Does it make sense to everyone? Please let me know, take a +1 in the chat. Because modulo is always for values that are greater. Like if I have, let's say 10 and I take 10 modulo 3, that will be equal to 1. But if I take 1 modulo 3, that's just the same number, right? It's just the same number. So what we will say is, if a is less than m, we'll just take a into a modulo m directly. We don't even need the modular arithmetic here, basically. Okay. So if you just take a, if you take a square, if you have a square and you're taking a square, this is just equal to a into a modulo m. And that's it. This is a square, right? And guess what? Our entire thing over here, our entire modulo thing, for a to the power of b, this also applies. This also applies for a to the power of b, right? So what I'll say is a to the power of b is equal to a to the power of b by 2 whole squared. Now, let us say that we know a to the power of b by 2 is less than mod. Let's say that we know that a to the power of b by 2 is for sure is less than mod. Then all you have to do is at the end, we need to take modulo m, right? That's it. So if I know for sure that a to the power of b by 2 is less than m, then this is clearly just a to the power of b is clearly just a to the power of b by 2 squared modulo m, right? Because if I had this, then it would be a into a to the power of b by 2 into a to the power of b by 2 modulo m. And I don't care what these a to the power of b by 2 values are, right? As long as they are proper, then it doesn't matter to me. Because modulo, like if I take a to the power of 5 modulo mod, then basically I can take a to the power of a into a modulo mod into, I'll take this part into a modulo mod, right? So I can take this modulo mod and multiply it by this modulo mod. And then I can also multiply by a and take modulo mod. So I can multiply the whole thing modulo mod, right? So I hope this makes sense. This is clearly just a to the power of 5 modulo mod would be this a into a modulo mod, a into a modulo mod into a modulo mod, right? That's it. Okay, I actually need to take one more modulo over here. Modulo m times a modulo m. Now, you can confirm for yourself that none of these values will exceed 10 to the power of 18. This is to avoid overflow. Yes, Akash. So we are doing this generally to avoid overflow. But let's just say that we are just doing this, right? Let's just say we are doing this. Here we will take a into a, which should be some value like 10 power 18. It will be at most 10 power 18 because we know that a is less than 10 power 9 plus 7. So I'm just assuming that mod is equal to 10 power 9 plus 7 over here, which is the maximum value. Like no one will give you a modulo above that. So you don't have to worry about that. So we know for sure that a is less than 10 to the power of 9 plus 7, let's say. Then this will be up to 10 to the power of 18. Then I'll take modulo mod. So this would be around 10 to the power of 9 again. And again, I'll multiply by the 10 power 9 again. And now after this modulo, the value will again become 10 to the power of 9. Right? So this entire value will become 10 to the power of 9. Now I multiply by a again, which should make it 10 to the power of 18. And after that, again, I take modulo, which should make it 10 to the power of 9. Right? So this is basically how it works. Now, the best part is that what I can do is to calculate a to the power of 10. Let's say I want to calculate a to the power of 10. I can still take the same value. I can just say, copy this entire thing, right? Copy this entire thing. Put it over here again. Multiply it now. Multiply this, right? Multiply these two things. And take modulo once more. And there we go. We have got an a to the power of 10. We are not even doing anything extra, right? We are just multiplying this and then I will immediately say, okay, that's it. That's the modulo. Does it make sense to everyone? Is this clear? Is this clear to everyone? Any doubts here? Like if I have a to the power of 5 modulo mod, if I have a to the power of 5 modulo m, then clearly a to the power of 10 modulo m is equal to a to the power of 5 modulo m into a to the power of 5 modulo m, which is just a to the power of 5 modulo m squared modulo m, right? So here when I multiply these two things, I'm just saying, well, take the square over here, right? So I'm just saying this part over here, this will be the square. So I'll take this squared modulo m. So yeah, so if I'm just taking some value, any a to the power of b, and then I square it and I take modulo, that will be the version, like that will be the same thing. Like it will be a to the power of 10 modulo m. These two things will be the same thing, which helps a lot. Modulo is so flexible. You can put it basically anywhere. You can put it in any order. You can do basically anything. And it will always give you the same result, which is awesome, right? So that's very nice. So what I can say now is simply a to the power of b. This is so simple, by the way. Like if you want to get modular arithmetic from binary, modular exponentiation from our binary exponentiation is just a to the power of b equal to a to the power of b by 2 squared. And sometimes we'll take times a, right? This is binary exponentiation. But to convert it to modular exponentiation, all you have to do is take the same thing, say, take this modulo m, multiply this by a, and again take modulo m. Right? There you go. And that's it. This is modular arithmetic. All I did was multiply this part. I took the square, modulo this part, multiplied by a and modulo this part again. And that's it. This will always give you a to the power of b modulo m. Even if b is equal to, let's say, 10 to the power of 9. Okay, Nikhil, that's a good question actually. It's not a silly doubt. How do we know that a to the power of b by 2 is less than m? This is a good question, Nikhil. And the reason is actually pretty simple. It's because a to the power of b by 2, when I'm calculating this, this is also modular arithmetic, right? This is also modular arithmetic. Okay, okay, people are annotating again. Let me disable annotations and clear all. Okay, there you go. Now, we know that when I'm taking a to the power of b modulo m, and when I go to my child, the child is also going to say a to the power of b by 2 times a to the power of b by 2 modulo m. Basically, this is what it's calculating, right? It's calculating this over here. Now it's taking this, and it's saying this will be equal to a to the power of b by 4 squared, right? It will be a to the power of b by 4 squared modulo m times a modulo m. Like it depends. Like I'm always putting this value, but it depends. It depends on whether it's even or odd, but I know you get the idea. But basically, this is the value that I'm going to be inserting for a to the power of b by 2. Right, Nikhil? So this power function always returns a value modulo m. So it returns a value modulo m. This will happen until 1. This will happen until 1. Okay, let's actually take an example. Let's say I take 2 to the power of 10 modulo 5. Right? I want to take 2 to the power of 10 modulo 5. What I'll say is, well, this will be 2 to the power of 5 squared times, there's no times actually. This is 2 to the
Modulo
power of,
5.
yeah, modulo 5, yeah. So because this 10 is even, we don't do that. But yeah, you are exactly right. Okay. Now, then for 2 to the power of 5, I'll say this is 2 to the power of 2 squared.
2 square into
Yeah.
2. Yeah, I'm just following.
Modulo 5 times 2. Yeah. So we actually first take modulo again, my bad. So we'll first take modulo because otherwise it will be 3 values, right? What if it's like 10 power 9 squared and you take this won't overflow. So if you take modulo, this won't overflow, but if you multiply it by a again, this might overflow, right? So for every 2 values, you need to take the modulo. So I'll take 2 to the power of 2 squared modulo 5 times 2 modulo 5 again. Then for 2 to the power of 2, I'll go to 2 to the power of 1 and I'll say squared modulo 5. And for this, I'll say go to 2 to the power of 0, which is just 1, right? So this is just 2 to the power of 0 is just 1. So we take 2 to the power of 0 squared, which is just 1 squared times 2. So we'll take 1 squared times 2, 2 modulo 5, right? So we'll be taking modulo at the end anyway. So this will be the
Hello?
value. Yeah, go ahead.
Hello. Can we use modulo as many times you want?
So that's actually a good question. You can basically use it wherever you want, as many times as you want. It won't change the value. But if you can, try avoiding it. Like try avoiding using a modulo unless you have to, because modulo is actually a bit slow. Like compared to addition, it's very, very slow, but it won't make a huge difference. So like if you do it accidentally once or twice, if you add it once or twice, or even a million times, it won't make a difference, but it will like add up if you do it way too many times. So just try to avoid it, but don't try too hard. Like if you think that you might overflow, always put a modulo, but don't put it just because you can, right? That's what I'm trying to say.
Okay.
Yeah, let's say you took 2 modulo 5, don't take modulo 5 again, because clearly this is already modulo, right? So you don't have to take it again. And one more tip, by the way, when you guys are taking modulo, and if you know that the modulo is like 1e9 plus 7, always put a const before it. Always put const int modulo, right? If you know that your modulo is 1e9 plus 7, like if it's an integer, if they give you an input of this modulo, then you should not do this. If they give you the input of modulo, like let's say it's 5 or 7, then you cannot do this because input cannot be taken as const. But what you can do is say, well, like probably if it's like 1e9 plus 7, you should always put const, right? Because const makes your code much faster. Like constant mod makes modulo faster. So yeah. So if you take modulo mod now with a const value, it will be much faster. What is 1e9 plus 7? Ritika, it's basically just 1e9 plus 7 is equal to 1e9 is like 10 power 9 and 1e17 would be 10 to the power of 17, right? In most problems where there is a modulo, they generally give the number 1e9 plus 7. Like you can take any combinatorics problem or anything like that. You'll always see that the modulo is like 1e9 plus 7 or anything else, but basically it's some number like this. So yeah, that's why we are taking this. So generally when modulo is involved, it's probably 1e9 plus 7. Okay. Now, anyway, let's finish this thing. So we went from 2 to the power of 1 to 2 to the power of 0
Hello,
squared.
sir. Hello,
Yeah.
sir.
Yeah, go ahead.
Sir, we use only 10 power 7 or we can use any number for modulo?
10 to the power of 9 plus 7 is the value given in the problem. Generally in the problem, they give you a number like 10 to the power of 9 plus 7. If the number is like, let's say 99985 or something like that, I don't know. If it's any other number, then you should use that respective number. Don't always use 10 to the power of 9 plus 7. It depends on the problem.
Okay, sir.
Yeah. So use what they give you in the problem. But this is just a general value. That's why I'm using this. Okay. Akash is saying 2 to the power of 0 is already 1. Then what's the use of taking modulo 5? Okay. So the reason I did that is basically because I'm just doing what the code does. I'm not, I'm not doing this to make it easier for myself, basically. Like the code does that, so I'm doing that basically. Like, I mean, I haven't implemented it yet, but our general idea, what our general idea is that we'll take a to the power of b modulo m equal to a to the power of b by 2 squared modulo m, right? So this modulo m is always there. That's why I just took that again. So Akash, there's no reason for this. I'm just taking modulo phi at the end of everything. So I just put it at the end of 1 as well. Okay. So now we have 2 over here. For 2 to the power of 1 is 2. So I'll take 2 squared modulo phi, which will be 4, right? So this will be 4 modulo phi, which is just 4. Now I'll take 2 square here and substitute 4 here. And I'll take 4 square. Now 4 square is 16, right? 4 square is 16, we know that. So I'll take 4 square 16 modulo phi, which will be 1, right? 16 modulo phi, we know is 1. 1 times 2 is 2. Now 2 modulo phi is 2, right? So we'll just take 2 over here. Now we are taking 2 to the power of 5 squared. But we know that 2 to the power of 5 modulo m is just 2, right? Modulo 5, this is just 2. So what I'm going to say is just substitute 2 for 2 to the power of 5. That's what I'm saying. So for 2 to the power of 5, I'm just saying substitute 2. Now if I take 2 squared modulo 5, that's again 4 modulo 5, right? And now for 2 to the power of 10, I went to 2 to the power of 5, right? I went to 2 to the power of 5 over here. And I know that 2 to the power of 5 is just 4. So I'll take 2 for 2 to the power of 10. I'll take this squared. So okay, one second. So I'll take over here, I'll take 4. Okay, I think I made a mistake. In the last step, I made a mistake, sorry. So for 2 to the power of 5, I'll take 4. I'll take 4 squared, which would again be 16. And 16 modulo 5, that will be equal to 1. Okay, this is my final calculation. Let's see if it's correct. Okay, let's take 2 to the power of 10. Once again, it's not in fact correct. Okay, I think I made a mistake again somewhere. Let us see. Okay, let's just do this again. I think this was not clear anyway. So let's just do this again. This would be 2 to the power of 5 squared modulo 5. And I know for sure that this 2 to the power of 5, this will also be 2 to the power of 5 modulo 5, right? So this 2 to the power of 5 modulo 5. Now, 2 to the power of 5 modulo 5 is 2 to the power of 2 squared when I take modulo 5 squared modulo 5 times 2 modulo 5, right? Because this is odd. So 5 is odd over here. So I need to multiply by 2 modulo 5. Okay. Now for 2 to the power of 2, I'll take 2 to the power of 1 modulo 5. And I'll square this. And I'll take modulo 5. And since it's even, I don't need anything else. And for 2 to the power of 1, I get 2 to the power of 0 modulo 5 squared modulo 5. And since this is odd, I'll take times 2 modulo 5. Okay, now let's start evaluating. 2 to the power of 0 modulo 5 is clearly just 1 modulo 5, which is just 1. And 1 square is also 1. And 1 modulo 5 is also 1. 1 times 2 is 2. 2 modulo 5 is just 2. So at the bottom layer, we clearly know that this is just 2, right? And that's correct. So for 2 to the power of 1, if I take 2 to the power of 1 modulo 5, well, that's just 2 modulo 5, which is equal to 2, right? So this is correct so far. Now I will take this 2 and I'll plug it into the above value. So I'll plug it into the above value. So what I'll get is this is 2. So 2 modulo 5 is just 2. I know that. So this entire thing was just 2. Now I'll take 2 square, which would be 4. And I'll take modulo, right? So I'll take modulo 5. 4 modulo 5 is just 4. Right. And we know that 2 square modulo 5, well, that's 4 modulo 5 again, which is just equal to 4, right? So far again, this is correct. Now, this 2 to the power of 2 modulo 5, this part, we know that this is equal to 4. So we just calculated this. We'll just put this over here. Now I'll take 4 square, which will be 16, right? So this will be 16. 16 modulo 5, well, this will be 16. 16 modulo 5 will be equal to 1. Now I'll take 1 times 2, which will just be 2. And I'll take modulo 5, which is just 2. Right. Okay. 1 second, let me go back. Am I doing something wrong? I think I might be doing something wrong. Okay, just give me 1 second to think about this. we are taking 4 square. Okay. So basically we know that if you take
2 to the
4
power of 5 is 2 to the power of
yeah,
2 into 2 to the power of 2 into 2 to the power of into 2, right?
sorry, could you repeat that? Sorry.
We have divide it 2 to the power of 5 is 2 to the 2 square into 2 square into 2, right?
Yeah. Yeah, okay. Okay, I actually got my mistake. Like what I was thinking was before I was okay, I made a mistake. Like I was saying that this value was equal to coming out to be 2, right? So if I take 2 square, like 2 to the power of 2 modulo 5 squared, this will be, I know this will be 1. So because that, I mean, if I take this entire modulo thing, this part will be 1, right? Because it's 4 squared, 16 modulo 5 is 1. 1 times 2 is 2, 2 modulo 5 is 2. So like for 1 second, I was confused because like if I take 2 to the power of 3 modulo 2, modulo 5, this will be equal to 1. This won't be equal to 2. This will be equal to 3, right? Like 8 modulo 5 equal to 3. But I made a mistake. I was actually calculating 2 to the power of 5. So that's my bad. Okay. If I take 2 to the power of 5, that's 32. Now 32 modulo 5, well, that's equal to 2. So that's correct. Okay. So this is in fact correct. So if you take 2 to the power of 5 modulo 5, that's equal to 32 modulo 5, which is in fact equal to 2. So this is completely fine. Okay. So this will be equal to 2 indeed. That's correct. Now I'll take 2 square modulo 5, which should basically be 4 modulo 5, which I know is just equal to 4, right? So this part is just equal to 4. Now, well, 1 second. Yeah, that is 2 to the power of 5. Okay, so this will just be 2 to the power of 2 modulo 4, modulo 5, which is equal to 4. And this entire thing is 4. Okay, now what is 2 to the power of 10? Well, that's 1024. And if I take 1024 modulo 5, you can see that that is in fact 4. Right, so we did get the right answer. Okay, there you go. So I did make a small mistake, my bad. Okay, Ankit is saying how to identify whether we have to use logarithmic or binary exponential. Okay, I think you're confusing this a little bit. Like it's modular exponentiation, or binary exponentiation. So modular exponentiation is only used when you want a to the power of b modulo m. And binary exponentiation is used when you just want a to the power of b. When there is no modulo m factor involved, you use binary exponentiation. Now, it's very easy to convert each of these, by the way. So here, instead of returning half power into half power, I'll just return half power into half power modulo mod. And over here, instead of returning this, I'll take modulo mod over here and modulo mod at the end as well. Right, so this is it. So I'll convert this. And in case a is greater than mod, if in case a is like, let's say, 10 to the power of 10, right? In this case, this won't work properly. So what we can do is at the beginning, we can just say a modulo equal to mod. And this will also work fine. Like this won't make any difference, right? So basically, it's like if you're taking a to the power of 5, then that's a into a into a into a into a, right? Like it's just the products of a. And the best part is that what you can do if you want to take modulo is just say that, okay, this a over here, I can just say this is a modulo m. So I'll just say this is a modulo m. Then I'll multiply again by a modulo m. And so on, right? And this won't affect my answer at all. I'll just repeat this for 5 times. And I'll again take modulo m at the end. That's still a different matter. But still, this won't affect my answer. Again, that's the neat part about modulo. Like you can use it basically however you want and it won't affect your answer. So what I can say is just I'll take a modulo equal to mod. Now, one thing you should never do is take b modulo equal to mod. Never take b modulo mod. This will absolutely not work. This will not at all work. Because, for example, let's say you want to take 2 to the power of 10 modulo 5, right? We know that this was equal to 4. But what if we took 10 modulo 5? That will just be equal to 0, right? 10 modulo 5 is just equal to 0. So that will just be 2 to the power of 0. And clearly this is equal to 1, right? So this is not correct. Don't do this. Never do this. What you can do instead is just say, well, I'll just take a modulo equal to mod. B is never moduloed. Only the value you are multiplying is moduloed. Because b is not an actual number. B is not an actual number. B is just a representation of the number of times you are going to multiply this, right? So if you just write this out fully, if you write out this product fully, you'll see that there is no B here. There is no B, right? There's no phi over here. Phi is just an imaginary number that we use to make this simpler for ourselves, right? So you should never take the modulo of B. Always take A modulo equal to mod. So if B is equal to 0, return 1, A modulo equal to mod, then you'll say half power equal to power A comma B by 2. And I know that this value will surely be modulo. So I know that power A comma B by 2 will always be less than mod. I know this because, well, this value is going to return a value that's already modded, right? So I'm always modding this before I return this. I'll take half power into half power modulo mod times A modulo mod, right? So yeah, okay. Is this clear to everyone? Also, one thing I could do if I wanted is say A modulo mod inside, and I could remove this, but it's not necessary. You can do it however you prefer. Like either way is fine. Like instead of taking A modulo mod equal to outside, in the outside, you can just do this inside over here. You can also take times A modulo mod inside, and that won't affect the answer at all. Okay, let's make sure it works. Let me see how. Also, let me make mod equal to 5 so that we can test this easily. Let's say I output power 2 comma 10. Let's see if this works. And there you go. I got 4, which is correct, right? Let's say I take 10 to the power of 9 plus 7. In this case, it should just output 1024. Why were we using A modulo mod? We were using it so that if A is greater than 10 to the power of 9 plus 7, so if A is equal to, let's say A is equal to like 10 to the power of 12, then I'm taking mod here, right? A half power into half power modulo mod. So this part over here, this can be at most 10 to the power of 9 plus 7. So it can be approximately 10 to the power of 9. But if I multiply by A without taking modulo of A, then what will happen is that we'll get 10 to the power of 9 into 10 to the power of 12, which will overflow. So since this is overflow, I can't use this. So yeah. Okay, cool. Now, does it make sense to everyone? Any doubts here? Is this completely clear? Any doubts? Okay, I'll just wait for a second. If anyone has any doubts, please do let me know. Like in the modular arithmetic, if something wasn't clear, you can let me know. Okay, I'll just wait for a second. Okay, I'll just go get a glass of water. If anyone has any doubts, you can let me know at any point, by the way. So yeah, so we'll be continuing in like 1 minute. Okay, fine. I guess we can move on then. Okay, actually, Mritika has a doubt. She's asking, why are we giving modulo mod here in the power function? So the reason I'm doing this is because I want A to the power of B modulo M. So I just discussed this entire thing because I wanted modular exponentiation, right? I want A to the power of B modulo M. Right, Mritika? So I want to take this basically. And so I'm just, I'm just, for that I'm moduloing, right? That's it. Like, if I want to do this, I have to do these parts. Akash is asking, can we also take half power into half power modulo mod into half power, half power modulo mod. Okay, he's asking like this. Half power modulo mod into half power modulo mod. This is completely fine, Akash. You can also do this in the second statement, obviously. But the thing is, this is pretty unnecessary. Like we already know that half power will be less than mod because, well, power of a comma b by 2, this will always return a value that is already taken modulo of, right? This will return a proper value. This will return a to the power of b by 2 modulo m. So if it returns a value of a to the power of b modulo m, then basically b by 2 modulo m, then basically, well, if that's already modulo, right? So this half power is already modulo. So I don't need to take this part. But you can do that. It won't make your answer wrong. Yes, Britika, we are calculating a to the power of b. We are calculating a to the power of b modulo m. And for that, we need a to the power of b by 2 modulo m, right? So I'll take this part squared. And if necessary, I'll also multiply by a. Will there be a change in answer if we use modulo more than required times? No, Aditya, it won't change your answer at all. For example, if I take another modulo over here, let's just say I decided to put a modulo over here. And let's say I wanted to modulo this as well. And let's say I want to put a few more over here. This will not change the answer at all. This entire thing it will still stay the same answer. And I can even take it over here if I wanted. If I really wanted, I could even take it over here if I wanted. And this won't change anything.
So we started this by doing like binary exponentiation, right?
Yes.
But we are using the when the number is big, we're using modular arithmetic in binary exponentiation, right?
Yes, exactly.
Okay, got it. Yeah.
So to take power of very large numbers, we can use modular exponentiation.
Yeah. So this is basically modular multiplication of binary. Like we're using modular multiplication method in binary exponentiation.
Exactly, exactly. So because exponentiation is nothing but repeated multiplication, right?
Right. Yeah.
So that's exactly why we are using modular multiplication inside this.
Okay, got it. Thanks.
Yeah. So we can use modulo as many times. Yes, you can, Aditya, but it will make your code slower if you use it too many times. So don't do that. Like just use it the required number of times. One or few more extra is fine. For example, let's say like, for example, Akash was asking, can we also take half power modulo mod into half power modulo mod? This is fine. Like if you do this, it's okay, right? It's not necessary, but it will be a tiny bit slower, but it will make no difference. So yeah, if you want, you can do this. If you are very paranoid, you can do this. It won't affect your code much, but don't do it unnecessarily. Like if you already took modulo, like you don't need to take modulo right after that, right? Obviously, you don't need to do this. This is completely unnecessary. So yeah, it's okay if you do it, but prefer using as less as possible.
No, like can you go back to the first for the changes of module, the original statement that you made? Yeah. We're actually using it only once, right? Then it goes on getting repeated because of a recursion, right? We're using only modulo once. That's the formula of modulo multiplication, right?
Yes.
Yeah, right. Like we can't use more, like we're not using modulo as many times as we want intentionally. Like we are using it in the first line and then it goes on. It becomes like a recursion. Yeah.
Exactly.
Yeah.
Okay then. Yeah, I hope this was a cool concept to learn because you can see how fast this makes our code, right? Instantly. Like this is also very intuitive. Like your brain would do this. Let's say if you were asked to find 2 to the power of 100 or something, right? Then you would say, oh my God, this is too much to calculate by hand. What if I just calculate 2 to the power of 50, right? This is something we all do. For example, we might also do, well, I want to calculate 2 to the power of 10. Okay, for example, I have remembered the value of 2 to the power of 10. I have memorized it. I know this is equal to 1024, right? So I can just say, okay, instead of taking 2 to the power of 10 from scratch, I'll just take 2 to the power of 100 from scratch. I'll take 2 to the power of 10 into 2 to the power of 10 and so on, right? I'll just keep multiplying this repeatedly. So I might do this once, and I'll think, okay, wait, I have done this once. And if I do it again, it will give me 2 more times, right? So this is the same thing 2 more times. So I'll do that again and again and so on. So like basically it's like we know, right? We know like our brains would do this, but putting this into code is the hard part. Like our brains are good at efficiency, good at efficiency and stuff, making things faster, etc. Right? So it does things very fast, But the issue is we just don't realize stuff that it does. So here it does do this. Okay. Ankit is saying, can we have the pre-written code? Yes, we can. You can put this in your template, Ankit. That's totally fine. So you can put this in your template. Okay, fine. I guess we should move on then. Okay. So the next thing that we are going to be discussing is GCD. So yeah, I guess everyone knows what GCD is basically. It's just the, well, greatest common divisor, right? Obviously, GCD is just the greatest common divisor of two numbers A and B. And LCM is the least common multiples of two numbers A and B. For example, let us say I have 10 and 25. Then the GCD is going to be 5, right? So because 5 divides both of them. So that's the GCD. Now let me take, for example, 16 and 27. In this case, there is no GCD. So GCD is just 1 because there's no number that divides both of these values, right? So for 16 and 27, it is not possible to have a GCD greater than 1. So the greatest common divisor is just 1. Okay. Now, how do we calculate the GCD? So in school or something, you might have, you might know that you just write down all the factors. Like you'll write 1, 2, 4, 8, 16, something like this. Or for 10, let's actually take 10. You'll write 1, 2, 5, 10. And for 25, you take 1, 5, 25, right? Now you'll say, okay, these are the common values. So I'll take this. This is my greatest common divisor. But there is an issue with this method. This method is actually extremely slow if you actually try to do this in code. Let us say we want to find the GCD of 10 to the power of 9 and 10 to the power of, let's say, 14 plus 100 and 100, right? Something like this. I don't know. Like, let's just say I wanted to do this. Now, what's the GCD? Well, if you were to do this method, first I'd have to factorize the first number. And what's the time complexity to factorize? We discussed this in the last class. What's the time complexity to find all the divisors? What's the time complexity to find all the divisors of a number? No. Okay, log n, Akash, is for sieve, right? So sieve is for prime numbers. Square root of n. That's right, Ankit. So to find all the divisors of a single number is square root of n, right? Like log n is the constant factor for sieve. That's not related to factorization. And n square is not correct because we are not going through the n multiple times, right? Like we are just going through it till the square root. So I'll go for I equal to 2 to the square root. And then I'll say if n modulo I, so if n modulo I is equal to 0, then I is clearly a divisor, right? So I is clearly a divisor and n by I is also a divisor. So here if n modulo I is equal to 0, I is a divisor and n by I is also a divisor, right? Like we discussed this again. Like if you have, let's say 110, if you want to find all the factors, it would be 110, 2, 5, and then 5, 2, and then 10, 1, right? So you'll just go till the square root and you'll find out the second pair from here, basically. So this time the time complexity of this will be square root of n, clearly. Now, basically, if I take two numbers like this will be square root of 10 to the power of 9 plus square root of 10 to the power of 14. And if this was 10 to the power of 18, that's going to be square root of 10 to the power of 18, right? Which is going to be huge. This is going to take a lot of time. So we can't actually do this. We cannot do something like this. This is just not possible. So we cannot factorize the entire number, right? Factorizing the entire number is not a viable strategy. But luckily for us, Euclid, a person in the, some person, mathematician from Greece or something, he actually made a much more efficient method that still is used today. Like this is used by this, basically the fastest method to find the GCD now, right? This is extremely fast, I promise. So what it does is it simply says GCD of A comma B. If I have GCD of A comma B, it says that GCD of A comma B is just simply equal to GCD of B comma A modulo B. That's it. It just says this is the entire formula. Or you can also do this. Actually, both of these are the same thing. Like if you you can take B modulo A or A modulo B at the end. Like this is fine. This is also fine. If you take B modulo A, comma A, this is also completely fine. Right. But yeah, basically the thing is GCD of A comma B equals GCD of B modulo A comma A. And that's it. This is it. This is the entire solution, I swear. Like, this is also recursion, by the way. This will also go recursively. And basically, if B modulo is A is equal to 0, then like if B is equal to 0 at any point, then if A is equal to 0 at any point, then B modulo A over here, this is the answer basically. Okay, I'll explain this once again. Now, if I take, let's try run this with some examples. Let's say I take 10, 3. Right. So let's say I take 10, 3. Okay, let's actually take 10, 25. So the A is equal to 10 over here. B is equal to 25. And I'll take GCD of B modulo A, comma A, which should be GCD of A. B modulo A would be 25 modulo 10, which is equal to 5. 5, comma A. Right. So 25 modulo 10, I'm taking 25 modulo 10, which is 5. And then I'm taking A, which is 10. Right. So this is GCD of 5, comma 10. It's saying that the GCD of 25 and 10 is the GCD of 5 and 10, which says this is the GCD of 0 and 5. Right. So what it says is basically, if B modulo A is equal to 0 at any point, then the answer is A. Right. If B modulo A is 0, then we cannot repeat this anymore. Right. So if I repeat this once more, what will happen is I'll get GCD of 5 modulo 0, comma 0. And 5 modulo 0, we know that it doesn't exist, right? We can't divide by 0, we can't take modulo by 0. So yeah. So the final answer is that if A is equal to 0, then B modulo A is equal to 0, then the answer is just the second value. Okay. Now, I won't go through the proof of this. The proof is a bit too long and I do not want to go into this right now. But yeah, we have to take min of A comma B. The neat thing is, Nikhil, you don't actually have to do that, because let's say I have B equal to 25 and A equal to 10. Now what happens is that I'll take GCD of B modulo A. I'll take GCD of B modulo A. Okay, 1 second. Oh, wait. Okay, let me just reverse this. Okay. A equal to 25, B equal to 10. Now I'll take B modulo A, which should be 10 modulo 25. Right. This would be 10 modulo 25, comma. The second value would be, well, A, right? So I'll take B modulo A, comma A, which should be 10 modulo 25, comma 25, which, as you can see, has reversed itself. So if necessary, it can just reverse itself, right? And there you go. That's it. It has reversed itself if it's big. So yeah, that's the neat thing. GCD doesn't even need that. And this is also very simple to implement. All you have to do is say in GCD of int A, comma int B. Now I know that if A is equal to 0, we return B, right? So like if the first value is 0, if this first value is 0, then I cannot take modulo again. I am not able to take B modulo A. So what I'll say is if A equal to 0, return B. And otherwise I return GCD of B modulo A, comma A. And that's it. There you go. This is the GCD function. This is the entire GCD function. Now, let me show you some examples. Let's say I take 10, 25. Samatyas, the underscore GCD function does use this method. It's very fast. So I'll come to that in a second. But yeah. So if you take 10, 25, you can see that it gives us 5. Let's say I take 10, 26. This should be 10. Sorry, this should be 2. Or here, this should be 2. Let's see. And there you go. It is in fact 2. Now, let us say I take 115, 198. I don't know what this is, but let's see. It's probably 1 actually. Yeah, there you go. It is in fact 1. And so on, right? I can do, like, I can take any number. Let's say I take 10 to the power of 9 or even more. Okay, what's this? This is 10 to the power of 10. Okay, so I'll just take 10 to the power of 17 this 10 to the power of 18. Okay, that's also fine. And 10 to the power of 18 and 2 into 10 to the power of 18. Now, clearly the answer is 10 to the power of 18, right? Like, if I take GCD of 10 to the power of 18 and 2 into 10 to the power of 18, clearly the GCD is 10 to the power of 18. And you can see that this was almost instantaneous. Now, let us see how many times it actually runs this. So every time I go through this GCD function, I'll just do count plus plus. This will tell us how many iterations it did, right? And well, you'll see that the number of iterations is just 2 over here. 2 or 3, I don't know, but yeah, it's 2, right? So basically, we got 2 into 10 to the power of 18. Then we went to the, we took modulo, it should be 0, and we took A, right? Why A equal to 0 returns B? Akash, again, that actually requires the proof. Like if you are asking like in a method of proof, then that actually requires the proof, which I'm not going to be discussing. It's a bit complex, but you're feel free to Google this and figure it out, right? Like you can Google this, there'll be many articles, but since we are running out of time, I cannot discuss it now. But when A equal to 0, it also logically makes sense that you cannot take B modulo A anymore, right? If you take B modulo A, that will be 5 modulo 0, which does not exist. You cannot take remainder of 0, right? Like remainder by 0. Like that's like dividing by 0. So that doesn't happen. Anirban, I'll share all the codes in the in the announcement channel after the class ends. Don't worry, Anirban. Okay, cool. So yeah, this is the entire GCD function. Now, again, I'm very sorry though, like I wanted to actually show this proof, but unfortunately, again, I don't have the time for it. Like we are already at the class, end of the class basically. But we will discuss, maybe we can discuss this in like an informal session or something in the future. But yeah, you can also Google this. There'll be many resources, like there'll be many good resources actually. Just search Euclidean GCD proof, Euclidean GCD proof. That's it. Yeah, Euclidean is indeed very simple. Yes. Okay. But you don't need to know the proof, by the way. Like there is no need for you to know the proof, but it will be good if you knew the proof. Like, you know, knowing the proof is not necessarily to, you know, use it in a contest, but rather just enjoy things, enjoy math by learning, right? And if you know the proof of some things, it will actually help you find the proof of other things as well. Like personally, I have used the proof of Euclidean algorithm to solve multiple problems, like multiple similar problems, not exact same, obviously. Like multiple similar problems have like a similar pattern. So yeah, it is possible that sometimes it will be helpful. So yeah. Okay, Akash says if A never equals to 0, then we'll keep running an infinite number of times. Yes, Akash, but A will always reach 0. It will always reach 0. Because if you take B modulo A, right? If you take B modulo A, then clearly over here, we know that, well, A, the B value at the end has to be lesser than A, right? So after this, we'll get some value C comma A, let's say. I know that C is definitely less than A, right? And after that, the next time we'll get again the same thing and it will keep decreasing, right? So it will keep decreasing by A minus 1. Are there any patterns in questions where GCD logic is required? Okay, so one problem was something like this. One problem was we will subtract, if you take this, we'll subtract A comma B, A minus B, and then we'll take B. So there was a problem like this. And this is like remainder is just repeated subtraction, right? This is just, I don't remember the exact problem actually, but it's like if you take two values and then you just swap them around, and you do it or something like that. I don't exactly remember the problem. Apparently, Samath saw this in a code forces contest. Okay. Samath, if you get, if you can find the link, you can share that in the TLE channel, I guess. But yeah. So yeah, but basically, yes, there are some problems like this. Like it generally requires you to swap them and then like do something like subtraction, for example. So yeah, that's basically the pattern. Okay, cool. So yeah, honestly, that's it. That's all there is to GCD. But one thing is that you can actually use GCD in C++. Like currently, GCD in C++ 20, I think, they already implemented GCD. Like you can just take GCD of any number like 5, 25 or something like this, and it will work fine. You don't have to define it yourself. You don't have to define the GCD yourself. But if you are using earlier versions, you can use __GCD. This will also work. Like underscore GCD will also work. If you can use normal GCD, you can also do that. Like it's completely up to you. Like both of them use the same method. Both of them use the very fast method. So you don't have to worry about that. So unlike power, GCD is very fast. Okay, cool. So yeah, that's honestly all there is to GCD. Now, I do have some codes here, like this recursive algorithm. This is something like just we discussed just now. And this iterative version is the same thing, right? So this iterative version, I'm just taking while A, basically while A is not equal to 0. So if A equal to 0, I'll stop looping this. I'll take temporary value equal to A. I'll say A equal to B modulo A and B equal to temporary value. This is just like saying B equal to A over here and A equal to B modulo A, right? So yeah, so I'm just taking temporary values and then I'm doing this while loop until it becomes 0 and it returns the value. Time complexity of this algorithm. So Samarth, the time complexity is just log n. So time complexity is log n, and that's it. So it's actually, I think I'm pretty sure closer to log 10n. So basically, like if you take 10 to the power of 18 or something like that, this should be approximately like 18 operations, basically. Like, you know, in the worst case, it will be a very, very less number of operations. Okay, actually, let me just Google this. Actually, I'm not very sure now. GCD time complexity, it is log n, but I don't know what base it is. So there is some base. I don't know what the base is, but it's log n for sure. Okay. Number of steps. There we go. Okay. Okay, this is actually not helping. Let me search worst case. Okay. Yeah, in the worst case, actually, the Fibonacci numbers are the worst possible inputs. I'll explain why. So let's say you're taking GCD of two numbers. For example, let's say you're taking GCD of, okay, let me write the Fibonacci sequence. You get 1, 1, 2, 3, 5, 8, 13, 21, and let's say the next one would be 34. Now, I'll take this Fibonacci sequence and I'll insert it into the GCD, right? So let's say I take the GCD of 21, 34. Now, what will happen is that the next number will be equal to, well, 34 modulo 21, right? So the next number will be 34 modulo 21, which clearly is equal to 34 minus 21, right? So here, since they are very close together, since the modulo is only going to divide once, well, we get the modulo as 34 minus 21. And we know that 34 minus 21 is equal to 13, right? So it's the previous number. So what we'll get is GCD of, from 34, 21, we will get the, we will get 13, 21. And this will be equal to GCD of 8, 13, right? Because now I'll take 21 modulo 13, which will be equal to 8. And this will be equal to GCD of, well, the next two numbers. And the next two numbers will be equal to, well, 5, 8, right? And so on. The time complexity is O of n. No, Ankit, you are very wrong. The time complexity is not O of n. It's always O of n, log n, actually. It's O of log n for sure. Like you can try this with any two numbers. Like see, the worst case is Fibonacci, right? And Fibonacci basically almost doubles every single time. Like Fibonacci almost doubles every single time. And the worst case time complexity is the amount of elements in this Fibonacci. Ankit, that is wrong. Actually, I don't know where you found that, but that's wrong. Because let's say you take GCD of x, 1. Let's see what happens, right? Let's see what happens when you take GCD of x, 1. Well, you'll just take GCD of, you'll take A modulo B. Okay, actually, you'll take B modulo A, which would be 1 modulo x. So it will be 1, x then. Then you'll take GCD of x modulo 1, right? You will take x modulo 1, it should just be 0, 0, 1, and you'll get GCD is equal to 1. So this is 2 steps. I don't know where you found that, but that's very wrong. Okay, cool. But yeah, the GCD time complexity is O of log n for sure. So yeah, it's a very good algorithm. And in the average case, apparently it's like I don't know. Okay. This is so weird. Okay, there's so much here. Okay, I do not know. Honestly, I do not know. I don't even want to process this. How can we tell it's log n? Because the Fibonacci sequence, this is actually the golden ratio. Like the Fibonacci sequence can be approximated by the golden ratio, which is like the some number 5 to the power of n or something like that. I am not very sure. Again, I'm okay. Let me just Google this. Fibonacci number, like estimate. And let's see the estimates. Okay, golden ratio. Let me search golden ratio. Yeah, you can see that it is defined with the golden ratio thing. Like, yeah. So this is basically the formula. There's 5 to the power of n minus 5 to the negative some weird thing. I don't know. But basically the idea is that it's going to be an exponential thing, right? Fibonacci sequence basically almost doubles every single time. So first it doubles, then it almost doubles, then it almost doubles again, and so on, right? So you can tell that this is definitely for like some base, like log n base some b, right? Some b. I don't know what that b is, but it is definitely some exponential number. Like I am not good at math, unfortunately, so I don't know what this exact value is, but you get the idea. You get the idea that this is the worst case. Fibonacci is the worst case because it has to go through this entire thing, right? So if I start at 34, for example, 21, 34, then it goes to 13, 21. So it from 21, 34, it goes to 13, 21, 8, 13, 5, 8, 3, 5, 2, 3, 1, 2. And at the end, it's 0. Like 1 does not appear again, it's 0, right? So yeah, so the Fibonacci sequence is the worst case scenario. And the Fibonacci sequence is exponential. So we know for sure that this has to be log n. Okay.
Will base b will be constant?
Yes, it will be constant. It's something related to the golden ratio. I'm not very sure.
Then why we are concerned about that? If it is constant, then we can remove it.
Oh yeah, we can actually remove it. Yes, but like Abhi asked, what's the like? How can you tell it's log n? I'm just trying to prove that there is some base. I don't know what that base is, but it's definitely a log. Like we do not care about what this log base is. It can be 2, it can be 10. We do not care. You're right.
Yes.
Yeah. So the time complexity is indeed O of log n. Okay. Is this clear to everyone, by the way? Any doubts? I know I didn't discuss GCD much, but you just need to remember the formula and stuff for now, like the method to do GCD. But you also can just, you can use the inbuilt one as well. That's also totally fine. But yeah. So the general idea is this. So the general idea is just that you take GCD of A comma B equal to GCD of B modulo A comma A. And the reason I took underscore here is because it doesn't coincide with the inbuilt GCD. But yeah. Okay, cool. Okay, I'll just wait for a second. Please let me know in the chat if you have understood with the +1. Sanchit and Abhi, Samat. Okay. They all said yes. Nikhil also understood, I guess. Okay, then. Manohar, nice. Okay. Okay, fine. I guess we can move on. Cool. So the next thing that we are going to be discussing is least common multiple. Now, least common multiple, this thing is very, very nice. Like LCM is very nice because if you take LCM of A comma B, actually this is simply equal to A times B divided by GCD. It's just A times B divided by GCD of A comma B. Right. I'll discuss the proof of this in a minute. But honestly, this is it. This is the formula. So you can find LCM if you know the GCD. So if you know the GCD, it's very, very easy to find the LCM. Right. So if you want to find LCM of A comma B, just take A times B divided by the GCD of A comma B. So we'll be discussing the proof of this in a minute. And Ritika is asking, will we discuss problems today? Unfortunately, no. This has taken way more time than I thought. So we won't be discussing problems today. But yeah. Okay. But one thing though about this LCM is that this only works for 2 numbers, like which basically means that you need to like do this 2 at a time, right? So you take LCM of A comma B is as this. Let's say you want to take LCM of A comma B comma C, right? Let's say you have A, B and C. Then what you do is first take LCM of A comma B and then you take LCM of A comma B comma C. Like you take this value, you take LCM of A comma B, and you put that in the LCM comma C, right? So these two will be the same thing, but this is the only way you can do LCM. Like for LCM, you cannot take A times B times C divided by GCD of A comma B comma C. This does not work, by the way. This will not work. So yeah. Okay, cool. So yeah, this is the LCM. Now let us discuss some properties, right? So let us discuss some properties of this. Okay. Now let us actually take what we discussed in the last class. In the last class, we discussed prime numbers and the exponentiation of that thing, right? So last class we discussed, like, if you have a prime P0, let's say, and you take power Q0 and you multiply that P to the power of 1 into Q to the power of into P to the power of 1 to the power of Q to the power of 1 times P to the power of 2 to the power of Q to the power of 2 and so on, right? If you do this, you can represent any number. Does everyone remember this? Does everyone remember this thing?
Yes, presents.
Okay, cool. Yeah, that's very nice. Now, GCD is actually very, very cool in a way, because let's actually name this A, right? The array of A only has prime numbers, and the array of B also only has prime numbers. Oh, actually, never mind. Okay, one second. Let me go back. So this will be actually the same prime numbers. So let's say I have P to the power of 0 into A to the power of 0. So instead of Q, I'll just use A. So this will be A to the power of 0, A to the power of 1, A to the power of, P power A to A2, P0 power A0, P1 power A1, P2 power A2, and so on, right? Now let me take this as a number X. X is equal to this number. Let me take another number Y equal to P0 power Q0 times P1 power P1 power B1 into P2 power B2, and so on, right? So these are the same prime numbers. Like, these are literally the same prime numbers. And now, what is the GCD of these two numbers is what I'm trying to find out, right? So what is the GCD of these two numbers? Well, it actually turns out the greatest common divisor is simply GCD G will be equal to P0 power min of A0 comma B0. Let me explain this. I'll show this by dry running this, and P1 will be min of A1 comma B1, and so on, right? This is just the GCD. Like, you'll take these two numbers, you'll take the minimum and you'll take the power. You'll take these two numbers, you'll take the minimum and you'll take the power, and so on. Now, let me show this with an example. Let's say we have a number 25 and I have a number 10. What is the GCD, right? To figure this out, what I'll do is just write 25 as 2 to the power of 0. 2 to the power of 0 into 5 to the power of 1. Okay, 5 to the power of 2. Now for 10, I'll write 2 to the power of 1 into 5 to the power of 1. Now I'll take the minimum of each. For 2, the minimum is clearly 0, right? I'll take 2 to the power of 0 multiplied by the minimum is clearly 1 over here for 5 to the power of 1. So I'll multiply that by 5 to the power of 1 and I get 5, right? And that's it. Now let me take another example. Let's say I have 2 to the power of 2 into 3 to the power of 7 into 4 to the power of 8. I have 2 to the power of 1 into 3 to the power of 9 into 4 to the power of 3. Now, the GCD is clearly going to be equal to 2 to the power of 1 multiplied by 3 to the power of 7 into 4 to the power of 3. This is the GCD actually, right? This is the entire GCD. Okay. Now, like Nikhil is saying, since GCD is a common factor, so we take min of A comma B, that's max common between them. That's exactly right, Nikhil. So how this works is because every prime number is distinct from each other, right? So no matter how many powers I take of 2, I will never be able to divide 3, right? And the issue is, if I take anything more than 2, if over here, if I take 2 to the power of 2, for example, I won't be able to divide the first number, right? So if I take 2 to the power of 2, I won't be able to divide the first number. Now, for the second number, if I take 3 to the power of 8, for example, I won't be able to divide the first number, right? The first number will be indivisible. So basically, what I'm saying is, to take the greatest common divisor, all I'll do is say, okay, I'll take 2 to the power of 1, which is the minimum, because that's the only number that divides both of them, right? So 2 to the power of 1 is a prime number that divides both of them. 3 to the power of 7 is a prime number that divides both of them. And like, I mean, at least a prime power, right? So that's the prime power that divides both of them. 4 to the power of 3 is a prime power that again also divides both of them. And this is the largest value. So for example, if I take 4 to the power of 2, yes, that does divide both numbers as well. But we want the greatest common divisor, right? We want the greatest common divisor. So clearly you using 4 to the power of 3 here would be better, right? So this is how GCD works basically. So GCD works by just what you do is simply you just take the minimum of all the powers. Okay, is this clear to everyone? Any doubts here? Does this make sense to everyone, by the way? Please let me know in the chat with the +1 if this makes sense. Otherwise, please do, if you have any doubts, if you want me to repeat this, please do let me know. GCD is just the minimum of the prime powers, basically. Now, okay, fine. I guess everyone understands. If you don't understand, please do let me know, guys. Please do let me know. Like, I will explain it again. Okay, Pial. Which part do you want me to repeat, Pial? Which part do you not get? Taking min of the two. Okay, let me explain. Now the thing is, if I, for example, let's take 4 to the power of 8 and 4 to the power of 3. First of all, we can tell that these prime numbers are mutually exclusive, right? So if I take these prime numbers separately and I multiply together the answer, this would clearly be the final answer, right? Like if I take for 2 I find some answer, then for 3 I find some answer, and for 4 I find some answer. I'll multiply all of them and I'll get the final answer. Oh wait, actually I am taking 4 over here. I'm stupid. Okay, I should take 5 or something. Yeah, 4 is not a prime number, right? So clearly we should not take 4. Okay. Yeah. Okay. So does this make sense, PR? Does this part make sense? We will take the prime number separately because they are exclusive, right? Like one prime number, no matter what this value is, even if this is 2 per 100, it's not going to affect the final answer. It's not going to, it's going to affect the final answer, but it's not going to affect these two, right? It's not going to affect the other 2 prime numbers. Is this clear, Pial? Does this not make sense? Okay. Now, what we are going to do is, let's say we have 2 to the power of 2 here. Now, let me take 5 to the power of 8 and 5 to the power of 3. Now, what I'll do is basically say the GCD, in the GCD for 5, I'll take 5 to the power of 2, right? I can either take 5 to the power of 2 or any value, basically any power of 5. But if I take something like 5 to the power of 2, clearly this divides both of them. This divides 5 to the power of 8 and this also divides 5 to the power of 3, right? But if I took 5 to the power of 3, that also divides both of them. So what I'll say is the answer is going to be at least 5 to the power of 3. Because if it's not at least 5 to the power of 3, then it's pretty stupid, right? Because we want the greatest common divisor. We don't want a value lesser than the greater one, like greatest possible one. So yeah, so 5 to the power of 3 is at least the answer. Now I'll say what happens if I take 5 to the power of 4. Then in this case, I won't be able to divide 5 to the power of 3, right? I will be able to divide 5 to the power of 8, but I won't be able to divide 5 to the power of 3 with 5 to the power of 4. So if I add 5 to the power of 4, I won't be able to divide 5 to the power of 3. So I'll say that, okay, the answer is less than or equal to 5 power 3, right? So answer is less than or equal to 5 to the power of 3, clearly, right? And 5 to the power of 3 is also less than or equal to answer, right? Because in the first case, if I go less than 5 to the power of 3, I can go to 5 to the power of 3, right? So if I take something less than 5 to the power of 3, I can just go to 5 to the power of 3 again. So clearly 5 to the power of 3 has to be at least the answer. So this has to be at least the answer, right? So the answer, like the final product over here, this has to be greater than or equal to 5 to the power of 3. So this answer over here has to be greater than or equal to 5 to the power of 3. But again, we also know that if this goes more than 5 to the power of 3, that will not be correct. So we know that 5 to the power of 3 is greater than or equal to answer as well. So if the answer is lesser, then it's going to be greater. If it's greater, then it's going to be lesser. And it goes to a point where you get to 5 to the power of 3. Because this is the best choice, right? You can take some examples to figure this out as well if this is not making full sense. But yeah, so basically the idea is that if you go above 5 to the power of 3, you need to go below, right? If you go above, then it's not possible. So I need to stay at 5 to the power of 3. If I go below 5 to the power of 3, that's not the maximum value. So I can just take 5 to the power of 3. So that's my answer. Okay, I hope this makes sense now. But yeah, this is basically GCD, right? And guess what? LCM is just the opposite. LCM is just max of these two numbers, right? Because in LCM, it's the least common multiple, right? So least common multiple would basically be over here. Well, to take the least common multiple, first I cannot take 2 to the power of 1, right? I cannot clearly take 2 to the power of 1 here, because if I do that, well, it's not a multiple of this number, right? So it's not a multiple of the first number. So in the LCM, if I take 2 to the power of 1, it's not a multiple of the first number. So I cannot take 2 to the power of 1. So I'll take 2 to the power of, let's say, 3. Now this is wrong, right? 2 to the power of 3 is wrong because this is not the least value possible. So least common multiple is 2 to the power of 2, right? So I'll take 2 to the power of 2 instead. Now I'll multiply that, well, with the second number. Again, I cannot take anything lesser than 3 to the power of 9 because that would mean that it's not divisible by 3 to the power of 9. But if I take anything greater, that will be greater than what I need. So the answer is 3 to the power of 9. And over here, this will be equal to, well, 5 to the power of 8 and 5 to the power of 3. Well, clearly it's 5 to the power of 8 because if I go below, then that's wrong. If I go above, then that's also wrong. So the answer for max, well, answer for LCM is just the max. Okay, cool. Now, this is just the LCM, and I am pretty sure that you can work the same thing out. I hope this makes sense. But yeah, and for GCD of A, B, C, if you're taking multiple values, then it's just GCD of A, B, C, etc. is GCD of A, B, and you take that within GCD of this, C, and you take that within GCD of this, another number, and so on. And for LCM as well, it's the same. So you'll take LCM of A, B, and you'll take LCM of that, C. So you'll take LCM of A, B, C, D, and so on. Right. So you'll take first A, B, then you'll take that, C, then you'll take that, D, and so on. So this is GCD and LCM. Now, one more thing is that GCD times GCD of A, B times LCM of A, B equal to A times B. Now this basically is the same as the previous one, right? Like LCM of A, B equal to A times B divided by GCD. So LCM is AB by GCD, or basically LCM into GCD equal to AB, right? Now let us look at the proof of this. Let's look at some proof of this. Let's say I have two numbers over here, and I want to take the GCD, right? Let's say I take the GCD of these two numbers. That will be 2 to the power of 1 into 3 to the power of 7 into 5 to the power of 3. Now, this is the GCD. And the LCM, well, the LCM is 2 to the power of 2 into 3 to the power of 9 into 5 to the power of 8, right? And we know for sure that if you take max plus min, if you take max of A, B plus min of A, B, clearly that's going to be equal to A plus B, right? Right. So max, I'm taking max of A, B, which will be either of these two numbers. It will be either of these two numbers. Let's say it's A, right? Then if I take min of A, B, that will surely have to be B, right? So if you take A, then that's the max is A, the min is B. If you take max as B, then the min is A, right? So what I can say is that if I take GCD times LCM, basically, what's happening is that we'll just take over here at the top, we'll take 2 to the power of A plus B. So A0 plus B0 or something like this. So I'm just taking min plus max, which is the same thing as, well, the total sum, right? The min plus max is the same as A plus B. So what will happen is if I multiply these two things together, notice that I'm just multiplying the original two numbers, except it might be in a different order. For example, over here, this is in a different order, right? So 5 to the power of 8, 5 to the power of 3 becomes 5 to the power of 3 and 5 to the power of 8. But even though the order is different, the values are the same, right? So the values are always the same. So basically what happens is that we get, well, GCD and LCM, the product of GCD and LCM equal to the total product, right? If I multiply these two things together, I get the original product. So if I do that, I just get the original product, and that's it. That's the answer. And that's how this formula also comes from. That's where the formula comes from. And finally, we have GCD of A, A plus 1. So this is a very important thing. Like many problems ask this, by the way. So this, just remember this, if you take GCD of a comma a plus 1, for any number a, this will always be equal to 1. Because let's try to look at how this would work. So if I take GCD of a comma a plus 1, this would be GCD of a plus 1 modulo a. This would be a plus 1 modulo a, comma a, right? Now we know for sure that a plus 1 modulo a, well, since they are very so close to each other, we can just say it's going to be subtraction. I don't even need to take modulo. I can just say this is just equal to subtraction, right? Now, if I remove this, I'll get 1 over here. And here you can clearly tell that the next step will get 0, comma 1. And so the GCD is 1. So GCD is 1 if you take consecutive numbers. So yeah, these are the properties of GCD and LCM. Okay, cool. And Ankit, yes, the class is almost over. You are right. Now, again, since it's almost over again, I'll just quickly go through this last point over here. I'm sorry for rushing this a little bit, but yeah. Okay, let me show you an example. So this OEIS over here, this is called Online Encyclopedia of Integer Sequences. And this is very nice because if you know a few values, let's say you found a pattern in some problem, right? Let's say you found a pattern and you get the pattern as this. Okay, let me just say for int I equal to 1, I less than or equal to 5, I plus plus. Now I'll output a completely random pattern. So let's say I output square root of I, int square root of I, plus int log 2 of I. And let me run this. This is some random thing that I came up with right now. I didn't even prepare this on anything beforehand. I'm just taking some random thing. Right, okay, let me do this for 10 numbers so that we get something useful. Okay, somehow I found this pattern, right? Somehow I found this pattern. Now what I can do is just take this, paste it over here. Oh, okay. Oh, 1 second. Please share PPT in Discord. Yeah, sure. I'll share the PPT in Discord. Yeah, I will do that. Okay, fine. It did not work for the sequence, but let me show you something else, I guess. Okay, let's say I take square root of I plus cube root of I, right? Let's say, how do I take cube root? Okay, I don't think I can take cube root right here. It's fine. So I'll take square root of I plus, let's say, I by 2, something like this, right? So some random formula. Let me just run this. Factorial. Yes, I could also do factorial, but I want to show that it can basically, it has almost all formulas. So if I paste this, you can see that it gives us some formula, right? Okay. This is, yeah, what are these values? Let me copy a few more, I guess. Okay, fine. So for some reason today it's deciding not to give me any formula that I come up with, but it actually does give us like a lot of different formulas. For example, if you have combinatorics, if you are doing combinatorics, n-choose-n or something like that, if you take anything random, right? If you take anything random, it has so many formulas. You can see, I just entered some random numbers over here. It can find so many different formulas, like it tells you so many different things, right? So there are many different things it can do. Factorial is a very simple example, for example, like if I take factorial of, let's say, 2, right? Okay, let's take combinatorics. Let's say I take n-choose-2. Let's say I take n-choose-2. This will be equal to n factorial divided by 2 factorial into n minus 2 factorial, right? Now, let us do this for 1. Let's do this for n equal to 1. That would be 1 factorial. Okay, actually for 1, we can't do this. Let's say we do this for 2. For 2, that would be 2 factorial divided by 2 factorial into 1. So this is just equal to 1. For 3 factorial, that's just equal to 2. This is equal to 2 factorial into 1 factorial, which is just equal to 3, right? Now, let's do the same for 4 factorial. So for 4 factorial, it's 2 factorial into 2 factorial, which should be 3 into 4, 12. 12 by 2 equal to 6. So that would be 136. Oh, apparently this will be just be equal to 10. The next value will probably be 10 actually. So let's try. We take 5 factorial divided by 2 factorial into 3 factorial. This will be equal to 3 into 4 into 5. Okay, actually that would be 4 into 5 divided by 2. That would be equal to 10. Okay. Yeah. So if I take this 1, 3, 6, 10, etc. 1, 3, 6, 10. 15. The next value will be 15. Basically, this is just n into n plus 1 by 2, by the way. You can also see that it tells us this is the binomial of n plus 1 comma 2, which is what I took here, right? I took n comma 2, n choose 2. Like it's taking n plus 1 because like it starts from 0 or something. But basically the idea here is, see, it tells us the thing, right? It tells us that it's also a binomial. So I just took some random binomial. It tells us that, and it also tells us the formula. And it also tells us the first few values. So you can even confirm with the same thing, right? So yeah, so you can see that this website is very, very handy when you have some patterns. So if you know some patterns and you want to find where this pattern is coming from, then you can probably use this thing and it will probably give you the solution. Okay, cool. So yeah, this is basically the idea. Now I have some problems here. I do have some problems here. Everyone can try these problems, by the way. Do try these problems by yourself. But yeah, like these will also be in the daily tasks. So don't worry if you like. I'll also be sharing the PPT too. Like these will be in the daily tasks. You can try this early if you want. But yeah. Okay, cool. So any doubts? Anything at all? And I know at the end I like rushed a little bit. I'm very sorry about that. But well, we are running out of time very quickly. So that's why I had to do that. Very sorry about that. Could you explain CU's time complexity? So we did that in the last class. You can watch the recording, but the time complexity is O of n log n. So you can watch the recording for that. So yeah. Okay, I just wait for a few minutes. If anyone has any doubts, please do let me know. I didn't understand. Okay, so basically, Akash, the idea is that if you are taking a CU, then in the first iteration, it will be n n by 2 loops, right? So the outer loop repeats for n times, but in the first iteration of the outer loop, it will be n by 2. In the second iteration, it will be n by 3. The third iteration, it will be n by 5, and so on, right? So it will be something like this. Chess engine. Oh yeah, sure, Krishna. I'll show you my chess engine. Okay. So it will be something like this, right? It will be the addition of all of these numbers. Now I'll factor out n. I'll factor out n and I'll get 1 by 2 plus 1 by 3 plus 1 by 5 and so on. Now it turns out this part over here, this is just equal to log n. Now don't ask me for the proof of this, but this part over here is log n. And so the total time complexity is n log n. So this is basically the idea. Okay, I'll just show you my chess engine, but if anyone has any doubts, please do let me know, by the way. Okay. Okay, fine. So let me just comment this out. Let me show this playing against itself. Now let me decrease the time. Like 5 seconds per move is a lot. So let me just decrease it to 1 second per move. And let me run this. And let's see how it plays. Oh, wait, I'm not starting from the original question, right? Sorry. Okay. Sriram, I actually named it Out of Stockfish. It's now called Out of Stockfish. Are you interested in GSOC? Like, you know, I'd prefer a Google internship, but GSOC is also fine. But I'm not 17. Like I'm only 17 this year, so like I cannot participate until next year. So I cannot do it this year, unfortunately. Yeah, I think I have made some bug because this is not castling right now, but whatever. Like it still plays decently well. I can fix the issue soon, but let me just go to Lichess and show you how it does it. First world problems. Yeah, I agree. Are you from IIT? Vineet, no, I'm like, I'm in school right now. Okay, so you can see that it plays this. And this is all the stuff that it played, by the way. Like it's not castling. I don't know why. Like I need to fix that. Like I just made a lot of changes today. So it's not working fine. But yeah, it should be easy to fix. So you can see that over here, when it attacks the opponent's knight because it knows that, we can save both of the pieces and stuff like that. So yeah. Yes, I did make it alone, Akash. Like this was entirely like an individual contest. So yeah, it should be even, okay, it's done now. Like black won apparently. This is very nice to see. What language and framework did you use? I used Python for this. Yeah. Somewhere it's actually not taking the thing properly. Okay, this should work fine now. Yeah, there you go. What technologies have you used? So the framework is basically like something called Negamax. So Minimax, Negamax, like they are all the same thing. So this is, let me show you. So first of all, I have this code over here. This is the full code, and there are a lot of constant values. You can see there are a lot of constant values. Vineet is asking, any of your personal experience with time management? None, because my time management sucks. Okay, so yeah. So first of all, we have the board over here. So the board has some stuff over here, and like, it just generates the board. This is update board. Like when I get a board, I can update it. And okay, I can just delete useless values. Then there is two board state. Like these are all internal APIs things. Like you don't have to worry about this. This is for a contest. So I'm doing this specifically for that contest. Like I'm not doing this so that people can play so far, but I am implementing that. Like human inputs can work like soon, but not yet. Then I have move, like it makes a move. Then I can unmove that. So if I made a move, I can remove that move. This checks if there's a check. This checks, this gets all the legal moves. This entire 150 line code gets all the legal moves. This is the evaluation, like position evaluation. And this is the engine part, like this is the actual engine. That was entirely the board part. So here I have like move ordering and stuff. Okay, this is a lot of things to explain. But yeah, basically this is using something called Minimax, which is generally the thing used to do board games. So if you are doing a board games, it generally uses this. How is it deciding the moves by itself? So the idea is that it will look far ahead, right? It will look 1, 2 to like it will look up to 4 moves ahead. This can look up to 4 to 5 moves ahead, and it will say, okay, 5 moves ahead, what is the best position that I can get? So the best position is decided with a static evaluation algorithm. So static evaluation is just going to take a board. It will just take a board and it will say, okay, this board is favorable for white, right? So it will say this board is favorable for white, or this is favorable for black. And it will also tell you how much it is favorable. So yeah, after a few moves, it figures out which position is the most favorable position. Now, obviously, it's not as simple as that. Like there are a lot of optimizations we can do. Like there's something called alpha beta pruning. There's something called delta pruning. There's something called PV line, transition tables, many different things, basically. Like there are many different things. Lots of maths involved. No, actually not at all, Anirban. Like there's not a lot of math involved at all. Like it's rather like heuristics. Like it's called heuristics actually. Vineet is saying all those AI concepts. No, they are not AI concepts, but people like to pretend they are. Like this is just a bot. This is just a bot. This is nothing related to AI. But if you see like someone saying that in their resume, they'll always put chess AI, right? But that's not correct. That's technically not correct. It's not AI. So yeah, any ML used? No, there's no ML here. Which contest? Oh, Krishna, this is like an internal like server contest, server-wide contest, a private server. Like, yeah, so it's for school students only. And it's a private server again. You can't join without an invite. You have one. Okay, I hope so. I hope I have one. But yeah, it plays decently well. Like even Stockfish doesn't hate its moves at all. Can you give me an invite? No, I cannot. I'm not the owner of the server. Like I'm far from the owner actually. You gave JE of any of those or any of those exams? No, I did not. Did you create it from scratch from logic till result? Yes, I did create it from scratch, but the logic I got from I obviously Googled a lot to figure this out. Like, see, there's this chess programming wiki which tells you like to search something, how do you search something? Like there are alpha, beta things, search tree, all of that. I had to read through all of these, many of these things. So there's iterative deepening, something called iterative deepening, all of that. Yeah. How much time did it take? It took me like 10 days. Oh, 10 days? No, actually, it took me like 8 days. But I spent a lot of time these 8 days, like the entire day for these 8 days. Can you share your LinkedIn profile? Sure. Yeah, I'll share it in the chat. Anirban is saying, how did you develop such great logic? Well, I just Googled this. I just learned from these, learned from what other people already did. And I just used that to be fair. But yeah, getting this to work was pretty hard. Like I had to do a lot of bug fixing. And still there are some bugs, like just now, again, the castling is not working properly. I don't know why. I'll figure that out in a bit. But yeah. Okay. Let me check right now, actually. Why not? So I'll check right now. Let's see if I can fix this. Oh, wait, 1 second. What's NXT? What do you mean by NXT? I didn't understand. Are you talking in about my code or something? Oh, okay. Like what's next? Well, nothing actually. The submission date is today, like today, end of the day today. So yeah, I hope like actually I already submitted a working version. Like I was just trying to make it better right now. Like only the last submission counts. I have made a working submission, like, and I've done it actually. Okay, let me check. I think I know the issue. Probably. Yeah, over here when I was getting this, I said you cannot castle. That's why it wasn't castling. But yeah, now you'll see that it plays with the castling as well. So yeah, you can see that black castled already. And white is likely going to castle soon as well. Yeah, there you go. So let me show this chess game, I guess. Okay, over here. Yeah, so it plays this. Okay. So if I run the evaluation, you'll see that actually Stockfish, like most of the moves are totally fine. Like if it will play this, it will play this, and so on. Like, see, the moves are not bad at all, right? Like if I wait for Stockfish's evaluation. Okay, why is it not evaluating? I don't know. I think Stockfish is lagging, but yeah, basically the point is that it plays very well. Like it's better than the decent, like average player. And the best part is that it never makes a blunder. Okay, how did you connect it to leeches? So basically I'm printing the moose here. I'm printing the moose over here, and all I'm doing is copy this. Like I'll just go to the end. What I do is just copy this, right? And paste it over here, and that's it. And you can see that this position is a draw now. Yeah, so if I just copy paste it, it comes here. How did you get to start with ICO? So Vineet, basically what happened is that like I started programming in 8th standard. Like my dad was like, I was homeschooled by the way. I'm homeschooled currently. And like, I mean, I'm not homeschooled anymore because my exams are over. But I was homeschooled and I had nothing to do like in my day. So my dad said, if you learn C++, I'll get you an Arduino, because for C++, like Arduino, you need C++. But then I came across CP and well, I came across ICO somehow. And yeah, that's how it started. What is ICO? Indian Computing Olympiad. It's an Olympiad for school students. So yeah, I think it's playing decently well, you can see. It cannot check en passant, by the way, like en passant doesn't exist so far, but it doesn't matter. It's very rare and generally it doesn't affect anything. So yeah. So you can see that it's playing decently well. Like Stockfish always suggests one of its moves. Like one of its moves is always suggested. And this is 1 second, by the way. Like I can also take 5 seconds. Like if I with 5 seconds, it will be way better. You didn't go to school? No, Akash, I did not go to school from 7th standard. Like till 7th standard, I went to school. How do you convince your parents to homeschool you? Well, you prove to them that schooling is pretty much useless. So, yeah. Back then, I was actually doing chess. Like, I was doing chess pretty competitively, actually. And, well, then, like, it was pretty evident that school was not helping. Like, I was doing nothing useful in school. So, yeah. Like, my parents were very open-minded. I'll be honest with you. My parents were very open-minded. In fact, it's my parents who actually suggested that I be homeschooled. Like, no, they found NEOS, they researched into it and stuff like that. Thanks a lot, Sanchit. Thank you so much. Will you go to college? Yes, Raja Jairam, I will go to college. So how you pass the grades? So in NEOS, you can actually write an exam. Okay, let me just stop recording actually.